when you look at this molecule, you don't know. I mean, when you look at any molecule, like if you see lemon, you don't see the structure. You never see that. Okay? There is no instrument that actually takes this picture. So how do you figure out that ethanoic acid looks like this? How do you figure out that it's got 2 carbon atoms? How do you figure out that it's got a double bond? So there's some techniques, and those techniques, they kind of give you bits and pieces of information about this molecule. One of those techniques is mass spectroscopy. You take a molecule, an unknown molecule, and you try and do mass spectroscopy. So these are some of the information that you can actually extract about a molecule. The first one is you've got you can figure out the number of carbon atoms. You can figure out the molecular mass, which is the MR. You can figure out, like, if you take acetic acid or vinegar, if you do mass spectroscopy, you'll get an idea of how many carbon atoms it's got. You'll get some information about the structure. You'll get some tiny bits and pieces of information about how the molecule actually looks like. What are the structures? Is there a CH3 in this? Is there an OH in this? Is there a acetyl bond in this? So you'll get tiny bits of information, bits and pieces about the structure. And one very important thing that you'll get is the number of Cl and Br atoms. So we're going to start with the first thing, and we'll try, and I'm going to tell you what a mass spectroscopy is. The working is not important. The concept is more important. So this is what mass spectroscopy is. Let's say you have a molecule of Cl2. So Cl2 molecule, there is this chamber which is known as the ionization chamber. What happens in this is that it's bombarded with electrons. So you've put a Cl2 molecule over here. You can put any molecule in there. Let's assume that we've put a Cl2 molecule over here. What will happen is that the Cl2 molecule will get ionized. It will form all sorts of ions. The Cl2 molecule would lose electrons, and it might form +1 ions, it might form +2 ions, it might even gain electrons and form negative ions, right? So that's the first thing, and that's known as a molecular ion. You'll turn the Cl2 molecule, which was a neutral molecule, into an ion by bombarding it with electrons so that electrons get knocked out of it. Okay, is that clear? Is molecular ion clear?
Yes.
Okay. But when you're bombarding it with electrons, the molecule might break down into pieces. Like the Cl2 molecule, the bond in the Cl2 molecule might break down. And that's known as a fragment, that a small, tiny piece of the molecule would also be created. In the case, in the Cl2 case, the tiny piece or fragment is going to be a Cl+1. So you'll have molecular ions and you'll have fragments. Maybe somewhere I would have done it with a bigger molecule, for example. If you do the same thing with CH3Cl and you bombard it with electrons, then a molecular ion would be produced, which in this case is CH3 Cl+1. And maybe the molecule breaks down into pieces. Maybe the CH3 fragment is produced, and that's a CH3+1 ion. Maybe a Cl atom breaks off. Maybe a CH breaks off, or a CH2 breaks off. So any random piece or fragment would break off, resulting in a tinier particle. So you'll have a big particle, and you'll have lots of tiny particles as well. This big particle is important because that's your molecular ion. This one is the heaviest. And then these are these tiny fragments. So the same kind of applies to Cl2 as well. You'll have a molecular ion and you'll have a tiny fragment. Okay. So is this part clear so far? Fragments and molecular ions. Hamza, clear? Okay.
Yes.
Sir,
Ji.
when the electrons are bombarded, it breaks down due to repulsion or something?
कुछ भी मतलब randomly ना कि let's say ये क्या ना कि you have okay, let's say there's a dot and cross diagram ठीक है over here. Okay, I've got a Cl atom and there's this other Cl atom and ये बीच में electron shared है. But that's what a Cl2 molecule looks like. ठीक है, यही है ना. तो उधर से electrons आ रहे हैं, ठीक है, a beam of electrons, charged particles, ठीक है. So any of the electrons can get knocked out. ठीक है, let's say it collides with this and this electron might get knocked out. तो क्या होगा? This molecule is now losing one electron, so it's a +1 ion. Is that clear?
Yes, sir.
अच्छा, अगर यही बीम ना बीच में से इलेक्ट्रॉन हो सकता है कि यहाँ से बीच में मिडिल से there might be electrons lost. So in that case, it would break down into, I mean, it would break down into smaller pieces. So the point is, it's a completely random process. There's no any type of ion could be produced, and not just one electron. Achha, over here I've written down +1. Remember this? There would be other fragments produced as well. Other molecular ion. I mean, there could be a +2 ion as well. There could be a -1 ion as well. But the beam filters out all other particles. The beam is only formed out of +1 ions. I'll also explain later how it does that, but right now just assume that the beam that is coming out of it contains only +1 ions. Okay? Now the next part is this one, that the beam of charged particles passes through a magnetic field. And you know in physics that if you pass a beam of particles through a magnetic field and they're charged, the particles, they get deflected. And the deflection is inversely proportional to mass. A heavier particle is going to be deflected less. A lighter particle would be deflected more. ठीक है, ये भी clear? Is this clear?
Yes.
Okay.
Sir.
So now, so how do you measure the mass of atoms? What you do is, you don't actually measure the mass of the atoms. You've sort of calibrated this. You measure the deflection, and the deflection will tell you the mass of the particle. You can convert this into an equation. There's going to be a constant. So, ये जितने भी atoms है ना, molecules हैं, उनकी जो mass है, that's known as the relative mass. So basically, you're not actually, I mean, there's no weighing balance where you could put an atom and measure the mass. What you simply do is you just measure the deflection, like how much it's getting deflected. If it's heavy, deflection would be less. If it's light, the deflection is going to be more. अच्छा, अब ये आपके particles हैं, and these are going to get deflected. Now, first information, very important, that you should know. And that's this information over here. कि आपके पास जो Cl का atom है ना, that's two types of atoms. There's 35 and there's 37. They're two isotopes. One has two more neutrons. So the mass of the particles is different. One of them is heavy and the other one is light. Now, what's the probability of getting Cl35? 75% of all chlorine atoms are actually Cl35. 25% of them are Cl37. Yani agar aapke paas you have 100 atoms and you have a sample of 100 atoms, 75 of them would be 35, have a mass of 35, and 25 of them will have a mass of 37. So the probability distribution is 3/4 chance, that's the probability of getting Cl35, and there's 1/4 chance of getting chlorine, which is 37. Okay, is that clear? That's the probability of getting both atoms, right? Is that clear?
Yes.
Yes, sir. What is the logic behind deflection? Is it heavier, then it will deflect less, and it's
हाँ,
light
मतलब
and
वैसे
deflect-
मतलब बेसिक फिजिक्स है ना कि अगर लेट्स से एक हैवी चीज आ रही है कि लेट्स से एक सड़क के ऊपर ना there's a truck coming, ठीक है, और एक जगह कार है और दोनों के ऊपर ना एक फोर्स, लेट्स से एक स्लेज हैमर बड़ा सा पड़ा हुआ है, दोनों के ऊपर एक फोर्स अप्लाई, कौन सी चीज ज्यादा डिफ्लेक्ट होगी? मतलब कार जो है वो लाइट है ना,
Yes, sir.
ट्रक को डिफ्लेक्ट करना तो
Calm down.
हाँ, तो क्लियर है कि हैवी चीजें they are difficult to deflect. Inertia वगैरह आ जाता है उसका, वो पूरा फिजिक्स के अंदर ना, you have कि F is equal to ma ना, तो अगर F सेम है और मास ज्यादा है तो एक्सेलरेशन जो होगी वो कम होगी ना. हैवी चीज को पुश भी करोगे ना तो उसकी एक्सेलरेशन कम होगी. लाइट चीज को पुश करोगे उसकी एक्सेलरेशन क्या होगी? ज्यादा होगी. ठीक है, क्लियर है?
Yeah, I got it.
अच्छा
Sir,
यस.
so what is the change of this? मतलब क्या changes आए हैं इस chapter में this year जो पिछले साल नहीं थे?
यही बस था, और तो कुछ नहीं है. ये एक्चुअली चैप्टर में चेंज नहीं है, ये ऐड हुआ है. ठीक है, मतलब चैप्टर का पार्ट ही नहीं है ये.
ये एडिशन हुई है इसकी?
हाँ, ये मतलब वो पिछले साल मास स्पेक्ट्रोस्कोपी ना वो था ना कि बस रिलेटिव एटॉमिक मास निकालनी है, दैट्स इट ना. ठीक है, तो अब तो वो है कि चीजें ऐड हो गई ना.
Sir,
Yes.
sir, this 75% being the CL35, is it just known or like
That's a
did
fact.
we?
That's a fact. Okay, if you pick any sample of chlorine,
Acha.
those 75% of that would be CL35 and 25%. And now different isotopes have different abundance, right? Abundance is their natural presence, right? For example, if I look at carbon, just a second, let's Google carbon's isotopes. So unki na, every atom has many different isotopes, na? So this is वैसी idea दे रहा हूँ कि every element has actually not one element. It's actually a bunch of isotopes. So let's look at this one. For example, there's carbon 12. So the probability of getting carbon 12 is 98.84%. Like that's the abundance. Approximately this is carbon 13. There's a carbon 13 as well. And the probability of getting that is approximately 1%. There's carbon 14 as well, and that's very trace. It's hard. It's very hard to actually detect it even. Oxygen ka bhi yahi hoga. Hydrogen isotopes are similar. Like if you look at isotopes of hydrogen, so 99.972% chance of hydrogen being hydrogen 1 is, I mean, that's a very high probability. The chances of getting deuterium, this is known as deuterium, this is the other isotope, that is almost zero, almost close to zero. This one is hardly detectable. So now the reason I'm sharing this with you is, okay, there's going to be variation in mass of the molecule. Why? Because this is water. Water has a mass of 18, but it only has a mass of 18 if the hydrogen has a mass of 1, right? But what if the hydrogen has a mass of 2? Then water will have a mass of 20, I think. Okay, so the point is that molecule ki jo mass hogi na, that is going to vary if the other isotope is present. Is the idea clear?
Yes. Yes.
Okay, but
Yes.
but that is not an issue with these elements. The reason we're not studying hydrogen is that hydrogen 2 ne aane kabhi nahi, it's a very low probability. Okay, even if there is a water molecule that has a mass of 20 because the hydrogen is 2, you're not going to detect it because the probability of getting that is very, 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 very low. Okay, so we don't care about the other isotopes. We don't care about the other elements. The reason chlorine is so special is that the chances of getting chlorine 37 is pretty high. It's 1/4. Okay, so that would result in a variation in mass of Cl2. Why? Because there would be 3 different masses of chlorine. I mean, the Cl2 molecular ion will have 3 different masses. One of them would be, either both of them would be 35, right? The first chlorine is 35 and the second one is 35. So the mass is 70. Or it could happen is that one of them is 35 and the other one is 37. So the mass of the chlorine ion would be 72. Or both of the chlorines would be 37 in the molecular ion and the mass would be 74. So there would be 3 different deflections. The heaviest one would be deflected less. The lighter ones would be deflected more when they pass through the magnetic field. Is the idea clear? You will part clear?
Yes,
This is okay. So now this is not the case with other atoms because unke isotopes, they're very, very rare. So we don't care about this. So in chlorine's case, you're going to get a lot of deflections. These are known as your molecular ion deflections. So I'm going to try and calculate the probability of, what's the probability? Okay, this has already been done. What's the probability of getting both chlorines as 35? So if you know basic math में क्या था कि जहां पे wherever you see an and, right? तो probabilities क्या होती थी? Multiply होती थी. ठीक है? If there's an and, probabilities get multiplied. So that means one of the chlorines is 35 and the second one is also 35. So then you're going to get 70. So that means the probability of getting chlorine 35 is 3/4. And the probability of getting the other chlorine as 35 as well is also 3 by 4. And if there's an and in between, that's going to be multiplication. So the probability of getting both chlorine 35 is going to come out to be, it's going to come out to be 9 by 16. Is the idea clear? Well, clear okay, probability. How did I calculate 9 by 16?
Yes,
Clear?
sir.
Yes.
Okay, so the next one is slightly tricky. This one, 72. What's the probability of getting a particle of chlorine ion which has a mass of 72? So what happens is either the first one is 35 and the second one is, so there are two sequences, two scenarios. One of them is either the first one is 35 and the second one is 37, or the first one is 37 and the second one is 35. In both cases, you're going to get a mass of 72. Okay, so it's either like if there's a Cl2 molecule, right? So when do you get 72? Either this one is 35 and this one happens to be 37, or there's another scenario, or the left one is 37 and the right one is 35, right? So they're basically two scenarios now. So यहाँ पे and and there's an or in the middle. Or means probabilities are going to get added up. So chlorine 35 and chlorine 37. What's the probability? 3 by 4 into 1 by 4. The other one is chlorine 37 and chlorine 35. What's the probability? 1 by 4 into 3 by 4. And there's an or in the middle. That means the probabilities are going to get added up. So there's going to be a plus sign in the middle. And that results, if you do the math, it's going to come out to be 6 by 16. Okay? You clear?
Yes, sir.
अच्छा, फिर अगला final वाला. That is, what's the probability of getting 74? You need both of them 37 and 37. So that's 1 by 4 into 1 by 4, that's 1 by 16. So that's the probability of getting that. Now, these are your probabilities. Okay, 74 detect करने का chance क्या 1 by 16. 72, the chance of detecting 72 is 6 by 16. And the chances of detecting 70 is 9 by 16, right? And what this translates into is that if you have 16 detections, like you detect 16 particles, 9 of them would have a mass of 70. 6 of them would have a mass of 72. And 1 of them will have a mass of 74. So, and this is always going to be the case. So the graph of mass spectroscopy kind of looks like this. This is how the data is represented. I mean, the same thing. Okay, this is nothing different. It's exactly the same thing. This is how it's represented. Okay, एक side में ना percentage abundance है कि कौन सा particle, how many times is it getting detected? So you'll have, well, this axis is mass to charge, which is basically mass. I mean, this axis is, E stands for charge. So the charge is always +1. So this is simply mass. So what's the ratio of the three particles? You'll get a detection at 70, which is this one. यहाँ पे detectors लगे होंगे. They'll be detecting particles, right? So you'll get a detection at 70. You'll get a detection at 72. You'll get a detection at 74. So there'll be detections. And what's the chances? The ratio of detecting 70 is 9. The ratio of detecting 72 would be 6. And this would be 10. Like, this is the ratio. It's 9 ratio, 6 ratio, 1. It's not that you're going to detect 9 particles. Maybe you detect 90 of them. So there would be 60 of these and there would be 10 of these. Okay, is that clear?
Yes.
Yes.
So it's 9 ratio, 6 ratio, 1, right? So that's the basic idea. And then you'll also have, so ये तो सारों को clear है, ठीक है, by once and for all. Is this clear? Molecular and Cl2. And the
Yes.
ठीक है. So अगला जो part है ना, that is कि you'll also have fragments, right? I told you that one of them would be your molecular ions. Those are going to be your heaviest ones. And then the molecule would split up into tiny pieces. Like it would be, अब Cl का piece बन गया, ठीक है, छोटा सा. So it would either be, now that will not have any variation mass. It would either, I mean, it will either be 35 or it will be 37. What's the probability of detecting a particle with a mass of 35? That's 3 by 4. What's the probability of detecting a particle with a mass of 37? That's 1 by 4. So इनका आपस में रेशियो क्या होगा? There's going to be some detection at 35. There's going to be some detection at 37. And the ratio of the particles would be 3:1. कि अगर 300 ये particles detect हुए तो 100 ये होंगे. ठीक है, it's going to be 3:1. अच्छा, फिर make sure you don't compare, you de-link the molecular ion with the fragments. Inka and these ones over here, they don't have any comparison. The reason they don't have any comparison is that the fragmentation is random. Maybe the molecule will fragment, maybe it won't. हो सकता है ना कि वो fragment ही ना करे, ठीक है, तो ये वाले होंगे नहीं particles, ठीक है. Or maybe what happens is a lot of fragments are produced. So in that case, the ratio would still be 3:1, except that the relative detections would be much higher. Okay, so maybe a lot of fragments are detected, or maybe very few fragments are actually detected. But whatever is detected will have a ratio of 3:1, because we know that the chance of getting chlorine 35 is 75%, and the chance of getting chlorine 37 is 25%. So इनके ratio को ना इनके ratio के साथ compare नहीं करना. Is that idea also clear?
Yes. Sir?
Yes.
So the Cl2 plus, like the ones on the right, the one with the 9:6:1 ratio, yeah?
Yeah.
Those are called the fragments, right?
These ones?
Yeah, what are these ones? These are the molecular ions.
Molecular ions.
Yeah, okay. And the left ones are the fragments.
The smaller ones are the fragments. Okay? That's the tiny pieces that are found when the molecule breaks down. Okay?
Yeah, okay.
Achha, now you're going to do the same thing with bromine. Okay, let's ignore this box over here at the moment. We're going to try and do okay, we didn't this one. Ye pehle kar lete hain. Now, exact same thing we're going to repeat this with bromine. What happens with bromine is that bromine also has two isotopes, which are fairly abundant. 50% is the chances of getting bromine 79, 50% is the probability of getting bromine 81. Ab isme ye ke the probability is 1/2, 1/2, right? So same exact thing, right? If you have a Br2 molecule, let's say I'll draw the ionization chamber, and there used to be a Br2 molecule, and it got bombarded with electrons, and it turned into anion. One of them is the molecular ion, this one. And this one over here is this one over here is the fragment, right? So exact same scenario, except that the probabilities are different, right? So it passes through the magnetic field. You get 3 molecular ion peaks. Why? Because the Br2 ion can have 3 different masses. It could either be both of them or 79. So the mass of Br2 plus 1 would be 158. It's a lighter version of the Br2 molecule. Or it could be Br2 plus 1. One of them would be 81. That's 160. Or both of them are 81. So the probabilities are exactly the same. I'm just going to change the 3/4 and 1/4 into half and half. It's 1/2 into 1/2, right? So that gives you 1/4. Over here, there are going to be 2 scenarios. Either the first one is 79 and the second one is 81, or the first one is 81 and the second one is 79. So it's half into half plus half into half, because both probabilities are 1/2, right? So that gives you 2/4. And what's the chance of getting 81? Both of them, that's 1/2 and 1/2, right? So that's 1/4. Okay, is this clear? It's the same exact math. Clear?
Yes.
Yes, sir.
Okay, the only difference is ye wala. The only difference is this one you've got. So that's the only difference. Okay, the probabilities are different. So now in this case, what will happen is the ratio of the detections would be, okay, middle one ki probability is higher, it's 2/4. Like if you have 4 particles, one of them would be this one. Two of them would be 160 and one of them will have a mass of 158. So your detector will be detecting something at 158, something at 160, and it will detect something with a mass of 162. And the relative heights or detections, the percentage abundance of the particles would go like this. It's going to be 1:2:1. So if it detects 100 particles of this, 200 would be these and 100 would be these. Is that clear as well?
Yes.
Obviously, there would be fragments as well. The BR fragment will have a probability of obviously 1/2. They have equal probability. So you're going to get two tinier peaks, both of them having an equal height, equal percentage abundance. Because they have the same probability. So you'll detect something at 79. You'll also detect something at 81. But they're going to have equal heights. So you clear it, this one, right? Clear?
Yes.
So, the next thing is, what do you do with this information? What do you do with this first information? What you do is, here is a CH3Cl molecule. अच्छा इससे पता क्या लगेगा? अच्छा एक थोड़ा सा I'll also add this thing. One information is that when you have the molecular ion is known as the M peak. Okay, that's, I mean, these are referred to as the M peaks. वो इसलिए करते हैं कि it's easier to remember the M terminology because actually telling someone it's 70 and 72 and 74, that's, so what they do is they call this M, the smallest molecular ion peak, that's known as M. इसमें और इसमें कितना difference है? +2 का, so that's M + 2, ठीक है, and this other one is M + 4. Okay, so the first one is referred to as M. So you don't look at the number, you just call it the M peak. This one is the M + 2 peak, and this one is the M + 4 peak. The same thing we did over there as well. Jahan pe we had bromine. Okay, I called all three are molecular ion peaks. I call this one as the M peak. इसमें और इसमें +2 का difference is that's M + 2 peak. That one is M + 4 peak. Is the idea clear? What is M? What is M + 2? What is M + 4? Is that clear?
Yes.
So it's just a terminology that is often used. Now, what do you do with this information? So I say you can extend this to 3Cls, you can extend this to 4Cls, but that would need, to calculate probabilities for 3Cls or 4Cls or 5Cls, you would need a computer for that. So you just stick to up till 2Cls. So first one, if a molecule has 1Cl, its molecular ion peaks would be 2. There's going to be an M peak and there's going to be an M + 2 peak, and the ratio or percentage abundance would be 3:1. And if a molecule has 2Cls, then it's going to have an M + 2, and M + 4 peak. And the percentage abundance or probabilities would be in the ratio of 9:6:1. So let me explain this. That's the main point. So let me explain this. Here's a molecule which has 1Cl, right? So it's going to have a molecular ion, which is going to be CH3Cl + 1. And it's going to have lots of other fragments, smaller fragments. I'm not interested in those fragments because they're going to be deflected more as well. So at the moment, I'm not interested in those fragments. I'm just focusing on the heaviest particle, which is the molecular ion. So, क्या mass होगी इसकी molecular ion की? Carbon is 12. Okay, I just showed you carbon doesn't really have a lot of isotopes. Hydrogen doesn't really have a lot of isotopes. So hydrogen is 1. Carbon is 12. Chlorine का issue आएगा. Chlorine, there's going to be variation in the masses of chlorine. So this molecular ion will have two different masses. 12 plus 1 into 3 plus 35 gives you 50. But if I use 37, the mass of the particle would be 52. One of them is my M peak, molecular N peak. The other one is also my molecular N peak, but that's M plus 2, right? So what is the probability of getting 52? The probability of getting 52 is determined by the probability of 37. What's the probability of getting 37? That's 1 by 4, right? What's the probability of getting 50? The probability of getting 50 is determined by the probability of getting 35. What's the probability of getting 35? That's 3 by 4. So in दोनों की relative heights क्या होंगे? So you're going to get a direction at 50, you're going to get a direction at 52, and the relative heights would be 3:1. That the chances of getting CL as 35 would be 3 by 4. The chances of getting CL 37 would be 1 by 4. Is that clear?
Yes.
One second. नहीं अभी मेरी आवाज कम है?
सर हमें तो ठीक आ रही है.
No sir, it's fine.
अच्छा ठीक है. बैकग्राउंड में नॉइज तो नहीं है यहाँ पे? उसमें बैकग्राउंड में मेरे साइड पे नॉइज है. चलो. अच्छा, now the point I'm trying to make is that you're not going to see all of this. Okay? You're not doing the probabilities. What you're just going to see is when you do a mass spectroscopy, you see this thing. That's it. I mean, this is the graph that there's a screen that shows you this thing, right? And all of a sudden you spot this thing. You see there's something getting detected at 50. There's something that's getting detected at 52. And the relative heights are 3:1. What does that mean? That simply means that the molecule has one CL. I mean, it's got one CL, exactly one CL. Okay? So is that clear? Okay. When you stand in front of the machine, you don't know what particles are being produced. You don't know what the molecule, you don't even know what this thing is. Okay? Because you can't even see this thing. Either to maine bana diya na ki there's a box which has CH3Cl. Now imagine there would be just a substance over there. ठीक है, विनेगर का एक छोटे से ड्रॉप्स डाल दिए बीच पे. So obviously you can't see what this is. You can't see what this is. You can't see what this is. So you'll be blind to all of this calculations. You wouldn't be calculating any probabilities. But what you'll get is the mass spectroscopy is going to output this thing. It's going to give you this graph. It's going to tell you that ये वाला जो particle है ना, there are 3 of them getting detected, and ये वाला जो है ना, that's 1 of them getting detected. So 3:1, that kind of means okay, you've got at least 1 CL. Is that clear?
Yes.
Bakiyon clear? Aisha, Main.
So how does this tell us that there's a CL? I don't get it.
Because you're getting 2 different masses. Why are you getting 2 different masses of the ball?
Because the rest of them have 1. Yeah, okay.
Because the rest of them, they don't really have isotopes, right?
Yeah, okay.
Okay, I just showed you carbon mostly is 12. Hydrogen is mostly.
Yeah, I forgot.
Okay.
Okay, thank you.
And the same thing. What if the molecule has 2 CLs, right? So if there's a random molecule which has got 2 CLs, right? So there's going to be a molecular ion, and there's going to be these lots of fragments. The molecule would break down into lots of smaller pieces. We don't care about the smaller pieces. We're just interested in the bigger fragment. So क्या mass होगी? It's going to be 3 carbons, that's 12 plus 12 plus 12, that's 36. Plus 6 hydrogens, that's 36 plus 6 hydrogens, कितने होते हैं? That's 42, right? So ये carbon or hydrogen, that's 42. There's not going to be a lot of variation in that. Okay? The variation would come with these 2 CLs. So there would be 3 different molecular ions. Either both of the CLs would be 35. We did calculate the probability of getting both of them as 35. That's 9 by 16. Or one of them is 37. That came out to be 6 by 16 earlier. Or both of them are 37. The probability of getting that is 1 by 16. Okay, so आपका जब mass spectrum होगा ना, you'll get this thing. You'll get something like this. Lots of tiny fragments, right? Lots of them randomly produced. Fragmentation is completely random. But there's going to be these 3 big peaks. These are your molecular ion peaks. मतलब इनकी values होंगी कि कहाँ पे आ रही हैं? M is 112. I mean, this is actually 112. Okay, it's given over here. This is 114 and this one is 116. But you'll just call them m plus 2, m plus 4. और उनकी relative abundance क्या होगी? ये 9 ये होंगे detect, 6 ये होंगे, 1 ये होंगे, ठीक है? This would be the ratio of the detections. When you see this thing, that clearly indicates, well, you wouldn't see any of this. You'll be blind to all of this. But when you see, when the mass spectroscopy shows you this, as soon as you see 9:6:1, that indicates that it's got 2 CLs. Okay, is that clear?
Yes, sir.
Yes.
और इसी को ना आप extend कर सकते हो bromine पे भी कि if there's one bromine, like I can, so if a molecule has one bromine, let's say there's CH3Br. So I'll just quickly extend this. So if it's got CH3Br, right? So iske molecular ions, there's going to be CH3Br plus 1, right? Okay, and it's going to have क्या होगा इसमें? इसकी mass क्या होगी? It's going to be 15 plus Br. There would be 2 of them. There's going to be M and there's going to be M plus 2. Why? Because either the mass would be 15, बल्कि उसको सारों को अलग-अलग कर लेते हैं. It's going to be 12 plus 3. It's going to be 12. So it's going to be 12 plus 3 plus 79, right? या फिर bromine दूसरा वाला हो सकता है. It's going to be 12 plus 3 plus 81, right? So what is the probability of getting, क्या बन रहा है? What is this? 15 plus 79, that's 94, right? And this one would be 96, right? What's the probability of getting this? 94, that's 1 by 4. Sorry, 1 by 2. What's the probability of getting 96? That's also 1 by 2. Yani if you, and there's going to be lots of fragments as well. So if you draw a graph of this, so how would the graph look like? Okay, there's going to be an M peak, which is at 94. Okay, or ek peak aa rahi hogi, that's going to be at 96. And the relative heights would be exactly the same because they have equal probability. ठीक है, दोनों की height जो है वो exactly 1:1 होगा. That's going to be exactly, it's going to be exactly the same. ठीक है, is that clear? And then obviously there's going to be lots and lots of fragments. Maybe there are fragments, maybe they're not. कि 15 पे भी fragment बन रहा होगा, कोई randomly 12, 14 पे बन रहा होगा. So there would be these random fragments as well. ठीक है? But this thing, the M peak and the M plus 2 peak will have a ratio of 1:1. ठीक है, तो यहाँ पे ये दिया हुआ है कि if a molecule has one Br, the molecular ion will have 2 different masses, one of them, and they would have equal probability. Is that clear?
Yes.
And the same thing,
Yes.
if a molecule has 2 Brs, then it's going to have an M plus 2, and M plus 4 peak. And I'll do one more quickly. Okay, let's say I have a molecule which is CH2, any molecule which has 2 Brs. So let's say I have this molecule. It becomes a molecular ion. अभी होगा कि या तो दोनों Brs जो है ना, that's 79. So that's 14. I think that's 14 plus, you could, somebody do the math, 79 plus 79, that's 158. What is 158 plus 14? That's 172. ये बता देना ये correct है कि नहीं है, ठीक है? That's your M peak, right?
That's 172.
So then you'll have an M plus 2 peak, which is going to be, it's going to be 14 plus 79, but one of the bromines would be 81. Or uske do scenarios honge. Either the first one is 81 or the second one is 81. So this one is going to have a mass of 174. And then you'll have an M plus 4 peak as well. Because both of them could be 81. So uski jo mass hogi na, that's going to be 176. Okay? And the probabilities, we already calculated that. Dono bromine 79, the probability of getting both of them, that's 1 by 2. This one is 2 by 4. Like one of them is 79, the other one is 81. And both of them 81, that's 1 by. So the first one is 1 by 4 actually. ठीक है, तो इसके अंदर भी वही होगा कि you'll be detecting different fragments and लेकिन molecular ion peaks, जो big peaks होंगी ना, जो heaviest, they're going to look something like this, the heaviest ones, or m plus 2 and m plus 4, 172, 174 and 176. They would have relative heights of 1:2:1. Or here obviously you'll have lots of small random fragments being produced. Okay, so is this clear?
Yes.
Yes.
Actually, this is a summary, but remember you have to know how to calculate the probabilities as well. Okay, so this is the summary, 1 BR, 2 BRs, and that's the other one. I share a link. This is the other one. If it's got 1 CL, if it's got 2 CLs. So the next we'll move towards carbons. Like you can also detect the number of carbon atoms in a molecule using mass spectroscopy. तो वो फिर वो भी इसी तरह कुछ, ठीक है, लेकिन वो नेक्स्ट टाइम करते हैं, ठीक है? चलिए, ओके। हाँ जी
सर, इन वीडियोस के लिंक्स कहाँ पे पड़े होंगे?
वैसे तो एक शीट मैंने शेयर की थी तुम्हारे साथ।
नहीं, वो A2 की शीट थी सर।
तो मैं AS की शेयर कर देता हूँ, इसी पे शेयर कर देता हूँ, ठीक है?
ठीक है,
चलो, ओके, टेक केयर, अल्लाह हाफिज।
Allah Hafiz.
Office.
Allah Hafiz.